MDM4U 8.1 continuous probability distributions. Previously, we've looked at distributions of discrete data, which has whole separate values, which we're looking at the outcome of. But with continuous values, there's an infinite number of values between any 2 points in a given range. So we're going to look at the probability density functions. For continuous data, the probability of an event is the area under the curve for the desired interval. The total area under the curve is equal to 1. So techniques in integral calculus help you determine the area underneath the curve. We have formulas which are simplified in order to be able to calculate these areas. Unimodal distributions, one peak. So here, each of these have one maximum. We talk about the distribution of a variable, or the distribution of a variable refers to what outcomes are most likely. In the case of a normally distributed variable, that means that we have one peak and it's equally likely to go to the left or to the right as far as the outcomes. Negatively skewed means that the tail is to the left and it's non-symmetrical. Positively skewed, think of where is the tail? The tail is to the right-hand side. So, if we were to think of bimodal distributions as having two peaks, this can occur when a population consists of two groups with different attributes. For example, the distribution of adult shoe sizes is bimodal because men tend to have larger feet than women do. So this peak right here could likely represent the size of an average woman's foot, and this is the size of an average male's foot. Not to say that there couldn't be a female's foot that's very large or a male's foot that is very small. It's just that we're talking about the distribution around the mean for each of these different groups. So, just to get some vocabulary regarding different types of distributions. Now remember, these rectangular shapes indicate that they are discrete values, but if you could imagine a smooth curve running through this to talk about the distribution for this chapter, that would be beneficial. So, this is symmetrical and unimodal. This is skewed to the right. Remember, where is the tail? This appears to have two averages, but they're not equally, they don't have an equal height, so it's non-symmetric, but it's bimodal. Uniform just means that each outcome is equally likely within a given interval. Skewed to the left, remember, when it comes to skewedness, you can identify by where is the tail. And then this is symmetrical because both peaks are, there's a mirror image in the middle, and bimodal because there are two averages, or two maximums. So uniform distribution. I want you to be aware of the fact that yes, we did cover uniform distribution with discrete data, but it changes slightly when we're talking about continuous data. So notice the following. A and B, we can consider that the range for the sample space where all outcomes are possible. And they're going to fall between these two values, A and B. If this is a rectangle, which represents the total probability, remember, the area underneath the curve for the sample space is equal to 1. If this distance here is B minus A, notice this is length B. If we take away A, we get the interval in between, which is B minus A. Then what would we need to multiply that by to get the length here? Well, B minus A divided by B minus A is equal to 1. And if we treat it like a rectangle, that's how we get this formula. So there are different forms of this equation, and I find memorization is going to work against you. It's better that you just understand this as an area of a rectangle, and the rest will follow suit. So notice that if it's less than, we're talking about a particular value, x. This is the component of the rectangle that we need, which is x minus a, this right here will always be 1 over b minus a for the height. Okay, and you can investigate that for each of these different types of intervals. So, for example, the first commercial break to happen in the first quarter of a football game happens anytime between 10 and 20 minutes. What is the probability that a commercial break takes place within the first 14 minutes? So, the interval, or the height of that rectangle will always be 1 over b minus a. But if it's happening between, and I'm going to steal this image, 10 to 20, we're wondering where x in this case is 14. So that being said, this length is 14 to 10. That's where you see this component. And the height is 1 over b minus a. That is 20 minus 10, which is 1 over 10. And we get 40%. All right, so this concept is fairly easy because we're talking about rectangles. This is an introduction to this topic, so make sure you don't breeze through the rest of this. Go through it on your own, but we're going to talk about more difficult concepts. So the exponential distribution. If the random variable being measured is the waiting time, then the exponential probability density function can be used to approximate probabilities. So, in the textbook, you may have noticed a different formula. What they provide you with is the probability density function, which is actually the curve itself, which is a complex calculation. Don't worry about that formula. It's not necessary in its utility. We are going to use the application using the following formula. So, we've discussed waiting time with discrete random variables, but let's discuss that further. The number of failures until a success occurs. In this case, waiting time is actually time, a continuous variable. Remember, between any two instances that are separate in time, you can always find that midpoint. There's always something in between any two given moments of time. It's continuous. In this formula, there's a variable k, which is equal to 1 over mu. This is the number of events per unit time. And there's two different versions. What we're going to do is look at this version, which is the probability that x is greater than a particular value of x is equal to e to the negative kx. So that tells you the area to the right of a certain point. And that area, if the total area underneath the curve is equal to 1, then in order to find the area on the left-hand side of a particular point, you would just use the total area minus this expression to get this area. And that's what's done in the second formula, 1 minus e to the negative kx. So, one last point. This waiting time, it's most likely, if this, all we need to know is the mean waiting time. And the distribution is as follows. It'll be highly likely that it happens in a shorter period of time, but there's a horizontal asymptote on the right-hand side because in theory you could have any length of time being possible for a waiting time. So, the average waiting time for a call center is 2 minutes. That's all the information that you need. What is the probability that a call is less than 3 minutes? So looking at our formula, selecting which formula is for less than, that is 1 minus e to the negative kx. And we substitute in our value. So the tricky part, k is equal to 1 over mu. In this case, it's 0.5. And our value for x is 3. So substitute and solve, and we end up with 0.7769, so about 78%. What is the probability that the next phone call will exceed 5 minutes? So here, notice that this is area to the right of the curve. We're asking for a greater than inequality statement. So that being said, probability x is greater than a particular value of x is equal to e to the negative kx. Our value of k is, well, mu is 2 minutes, so 1 over 2, we get 0.5. And x is 5. Substitute and evaluate. We end up with that outcome happening about 8% of the time. Now, one image that is not shown is what happens if we were asking for the likelihood that a time falls into an interval. Now, we don't have that given directly, but if you can consider that this expression is giving you the area to the right of a certain point x, then we can use this formula twice. So take the total area, and if we had a second point here, we could subtract that area to get the interval between, let's call this x1 and x2. So that being said, this is what is done in this question. We want to know the area to the right of 1 and 3. Notice that this smaller number for x is on the left-hand side because the area is to the right of that point. And then if we subtract the area of the second point, which is on the right-hand side, in this case 3 minutes, we'll be left with the component that we're looking for, the interval. Okay, so try these questions. If you have any questions, let me know. Take care.